Okay, Chemistry 3111, let's get started with Chapter 18, which deals with aromatic substitution reactions. And this is one of the longer chapters that we cover. And just as a reminder, the longest chapters in Chemistry 3111 are 18, 19, 20, and 21. So we're on 18 right now, and we have a little extra time allotted for this chapter. So we're going to start out in section 18.1 with electrophilic aromatic substitution. This is actually the biggest part of the chapter. I'm dealing with electrophilic aromatic substitution. And it says here that we already have seen how aromatic pi bonds are less reactive than typical alkenes. This was actually covered in chapter 17, toward the beginning of chapter 17, as a matter of fact. We said, okay, if you take some cyclohexene, so cyclohexene, and you treat that with bromine, you get an addition reaction, right? So this is an addition reaction, and you get anti-addition, so you'd form this compound plus the enantiomer. However, if you take benzene, well, you remember that benzene is aromatic, and so it's a very stable compound, and so it does not do an addition reaction. You get no reaction when you put benzene and bromine. Nothing happens at all. And again, it's because benzene is an aromatic compound. It has a closed shell electron configuration, which renders it unstable. However, if you add some iron to the mixture, so if you combine benzene and bromine, and then you throw in some iron, okay, so just a little bit of iron. And if you're wondering, just iron metal, yes, just iron metal, then you get what's called a substitution reaction. So what we're going to do is we're going to substitute a hydrogen atom for a bromine, okay, and that's why we call it a substitution, right? In this case, we're substituting H for the bromine, okay, so a substitution reaction, and we call this an electrophilic aromatic substitution reaction. And so what we're going to see over and over here is that when you put a benzene ring or an aromatic ring in the presence of a very powerful electrophile. So when we're talking about electrophiles, we're talking about strong electrophiles. So when we put them in the presence of a very strong electrophile, they will react. And it turns out that there's a reaction that occurs between the bromine and the iron. So, and this is just taken from the textbook. If you take bromine and you combine it with iron, you end up getting two equivalents, in this case, of iron 3 bromide. And the iron 3 bromide actually acts as, so this acts as a catalyst to lower the activation energy of this reaction. Now, in terms of synthetic utility, this whole concept of an electrophilic aromatic substitution reaction, meaning replacing a hydrogen atom on the ring for another group, so it says an aromatic proton is replaced by an electrophile. And in these cases, the ring actually acts as a nucleophile. Okay, so what are the types of electrophiles that we can substitute in place of our proton? Well, you guys know what a bromine is, okay? So you could make bromobenzene, you could put a chlorine in, you could make chlorobenzene. Now, if you're wondering, well, what could I do with those? You know what I think of when I see chlorobenzene or bromobenzene is a Grignard reaction, right? So then I could make a new carbon-carbon bond. I can also do what's called a nitration reaction and install a nitro group. I can do what's called a sulfonation reaction and put in this functional group. If you don't know this one, this functional group here, this is called a sulfonic acid. Sulfonic acid. And then, of course, you can put in an alkyl group. An alkyl group, I should write nitro here, just in case anybody's forgotten that. And then the last one, when you have a carbonyl followed by an R group, we call that an acyl group. So an acyl group. So an alkyl group, acyl group, sulfonic acid, nitro, and chlorine. And if you're wondering, you know, I understand what you can do with an alkyl group and an acyl group, maybe I could reduce that. But if you're wondering, you know, what's the point of the nitro group and the sulfonic acid, it will become abundantly clear as we progress through the chapter. But what do you notice about all of these reactions? What do they all have in common? You start with an aromatic ring and you end with an aromatic ring. And so aromaticity is preserved in an aromatic substitution, an electrophilic aromatic substitution reaction. Well, let's dig in deeper into this reaction here, okay? The bromination reaction, where we substitute a hydrogen atom for a bromine. And let's get back to this idea of mixing the iron and the bromine that I had written down a couple of slides ago. Okay, so this reaction here. Well, just by way of review, you know that when we combine cyclohexene, right? If you combine cyclohexene with bromine, and these little symbols here got erased. So this is supposed to be delta plus, and this is supposed to be delta minus, okay? But you know that when you combine those two, okay, as we saw a couple of slides ago, you get an addition reaction where you form the trans 1,2-dibromo cyclohexane plus its enantiomer. So we get an addition reaction. And why does that occur? It occurs because the pi bond in your cyclohexene acts as a nucleophile, and the bromine, the Br2 molecule, becomes temporarily polarized. We get a delta plus, a delta minus, right? And you don't have to draw the curved arrows right now, but these are the curved arrows for the mechanism. It looks something like this. You lose your leaving group like that. You form the bromonium ion, and then the bromide comes in, does nucleophilic attack, okay? If you're a little bit, shy or, kind of forget what I'm talking about, this is all covered in chapter 8, okay? Everything I'm talking about right now. But going through this idea of putting bromine in the presence of an aromatic ring, we said it doesn't react. However, what happens with that iron is when the iron reacts with bromine, you end up forming iron tribromide, or this is more properly called iron 3 bromide. In the textbook, they refer to it as iron tribromide, but it's iron 3 bromide. Anyhow, and this happens to be a catalyst. So it says here a Lewis acid catalyst is required to make the bromine more electrophilic so that it can be attacked by the pi electrons of the aromatic ring. So I want to stress this again, that the iron 3 bromide or the iron tribromide is the Lewis acid catalyst. And what do we know about catalysts is that they get recycled over and over. So when the iron and the bromine combine, it doesn't all get converted into this. Some of these are going to combine to make some of the catalyst, okay? But there's still going to be some Br2, some bromine kicking around. And so this is our Lewis acid. This is our Lewis base. If you've forgotten, a Lewis acid is an electron acceptor, and a Lewis base is an electron donor. Okay, so we form this complex, okay, here, and you see that they've drawn a couple of forms of it here where there's an equilibrium between this compound here where we have this Zwitter ion, and then the bromine breaks off to form this bromine cation. So in that case, you can imagine that this is a very, very powerful electrophile, right? Think about it. It's got a positive charge. It wants electrons really bad. So this is a very powerful electrophile. Now, sometimes if you're perusing the internet or if you're looking at some textbooks, they'll draw the mechanism of bromination, just drawing what's in the green box here, the bromine cation. That is okay. In our textbook, I think he usually draws the mechanism with this complex that's shown here between the Lewis acid and the Lewis base. And if you don't really follow what I'm saying here, trust me, it will become abundantly clear once we look at the mechanism. But the idea is that the Lewis acid reacts with the bromine, and now you end up with an even more potent electrophile. So it's so powerful that once you put it in the presence of the aromatic ring, the aromatic ring is going to act like a nucleophile. I totally get it if you're thinking, what aromatic ring? You just spent all of chapter 17 telling me that this was so stable. It is. However, if you put it in the presence of a strong enough electrophile, it is going to act like a nucleophile, and you're going to see a nucleophilic attack occur, and that's what is shown over here. Okay, so if you remember the complex that was formed between the iron 3 bromide and the bromine molecule was this one here. That is what they're drawing as our potent electrophile. Okay, it's a very, very, very strong electrophile. And when you put it in the presence of an aromatic ring, you get a nucleophilic attack. Okay, and once you do that, right, remember that this carbon has one hydrogen on it, okay, that I have drawn in red. It still has one hydrogen, but now you formed a carbocation, right? This carbon is sp3 hybridized now, but the one that's a carbocation is sp2 hybridized. And so what do you notice about this is that this is an allylic carbocation, right? You see there's an allylic carbocation right here. And so we can draw 3 resonance structures, and we call this the sigma complex. So the intermediate that's formed after the nucleophilic attack is highly resonance stabilized, right? You see there's 3 resonance forms here. Now, what do you notice is that this is aromatic, whereas the sigma complex is non-aromatic because it's got an sp3 hybridized carbon in it. So it definitely can't be aromatic. It's non-aromatic. And so what happens at the end, in the last step is that we get a proton transfer. Okay, so we see that we form HBr from this curved arrow here. We form HBr. And what's more important is that we restore aromaticity to the ring. So we go back to having our aromatic ring, we produce some HBr, and we regenerate our catalyst. So remember, this is our catalyst. Okay, and we regenerated it. So in step 1, the aromatic ring, which we haven't seen behave as a nucleophile until today, attacks the electrophile. You form the sigma complex. So sigma complex is going to come up about Avogadro's number of times in this chapter, the whole idea of a sigma complex. And then the deprotonation of the sigma complex causes what we call re-aromatization to occur. So we just regenerate the aromatic ring. And if you can follow this mechanism, if you can draw this mechanism, I got some good news for you. All of the mechanisms, I would say, in electrophilic aromatic substitution follow this pathway. Now, when you're looking at this mechanism, you might say, well, okay, this is great and everything, but why would this happen instead of just an addition reaction? Okay, well, there's a very good reason for that, and it's shown here on this reaction coordinate diagram. So this is free energy over here, Gibbs free energy, delta G, okay? And you can see that if you go from your starting material, which is your benzene, okay, which is over here, okay, then you form your sigma complex, and then you form your substitution product. Well, what do you notice? You notice that this is more stable than the benzene, and so in this case, your delta G is going to be negative, so this would be an exergonic process. Therefore, it is spontaneous. However, if you were to do the addition reaction, in that case, it would be endergonic, as it says up here in the notes. And so that would not be a spontaneous reaction. So let me write that word down here. So this is exergonic. When delta G is negative, it's an exergonic reaction. Whereas in the case where it's endergonic, in that case, it's going to be delta G is a positive number, like that. All right, so there you go. So that gives you a little bit of a thermodynamic explanation as to why electrophilic aromatic substitution occurs, because we end up with something that's more stable. Now, something that I've tried to mention to you several times throughout the course is that, we learn one way of doing a transformation, doing some kind of reaction. Then oftentimes we'll learn a second way of doing it. For example, I taught you the Swern reaction. I taught you pyridinium chlorochromate, PCC. I taught you the Jones oxidation, right? And these different conditions can be used to do the same things, right? Desmartin periodinane, etc. And so besides using iron as our Lewis acid, right? So iron reacts with bromine to form iron 3 bromide. You can also use aluminum tribromide as your Lewis acid. Aluminum tribromide is a very inexpensive compound. And so if you mix your aromatic ring with bromine and then you put in aluminum tribromide as your Lewis acid catalyst, so I know it's in the slides above, but we'll just label this Lewis acid catalyst, okay? Then you're still going to get a substitution reaction. And if you're wondering, well, what does the mechanism look like? It's going to look exactly like this one. The only difference is you change the bromine for an aluminum, the bromine for a chlorine and the iron for an aluminum. Everything else is going to look identical. And so if I go back here, you change your iron for an aluminum is all I meant to say. And so the mechanism would be identical to the bromination when you use iron 3 bromide. So it's the exact same mechanism. Sorry, I was getting ahead of myself. Is if you want to do a chlorination, the same thing applies, where you would just replace your iron with aluminum and your bromine with chlorine. So we could also use aluminum trichloride as a Lewis acid and put chlorine with our benzene ring, with our aromatic ring. And in that case, we undergo chlorination. So now what have we learned? We've learned 2 reactions. We've learned that you can do bromination. Okay, so let's back up. Where is it? I had it here concisely somewhere. Anyhow, I guess we could just say here, yeah, so we would say you could do this reaction, so bromination, you could do it with aluminum tribromide, or you can do it with iron 3 bromide. So those are two sets of conditions to do the exact same thing, bromination. Okay. Then for chlorination, we can use aluminum chloride to do that. Sometimes students will ask me, could you use iron 3 chloride to do that? Yes, I think it would work as well, but it's not mentioned. I don't think it's mentioned in the textbook. I think he uses aluminum chloride every time to do that. Okay, so that begs the question, well, what about fluorine and iodine? We're leaving those out because you know the four halogens, fluorine, chlorine, bromine, and iodine. Well, it turns out that these reactions only work really well for chlorine and bromine. Fluorination is actually a very violent reaction. It's exothermic, can cause an explosion, so we don't like that. And then iodination is very slow. It's so slow that it doesn't work well. However, with the iodination, I think there is an example that it shows you in the textbook, and I think it's question 18.1. They show you that if you take benzene, okay, so benzene, I'll just put a proton here for instructional purposes. If you combine it with iodine and copper 2 chloride, so CuCl2, you end up doing an iodination. Okay, so that there are conditions that you can use to do iodination, but in the textbook, I'm sure I know he asks a lot more questions about chlorination and bromination. It's a lot more common, but again, you can do iodination with iodine and copper 2 chloride. There's no mechanism provided for that whatsoever, so don't worry about that. All right, so if you want to look at the mechanism for the chlorination, so remember we had, what did we have? Let's write it down just to be sure. We had benzene, right, plus chlorine, and then we had aluminum chloride, and we formed chlorobenzene like this. Okay, so this is just the mechanism for the reaction. So it's, again, all you would do is replace your iron with aluminum and then your bromine with chlorine from the mechanism that we were looking at, 5 minutes ago. So what's the first step? The first step is a nucleophilic attack. You go from something that is aromatic to something that is not aromatic, your sigma complex. The sigma complex is resonance stabilized. You should be able to draw all of the resonance contributors. And then we get a proton transfer at the end. And of course, in this case, we'd form chlorobenzene plus HCl, plus you would regenerate your aluminum trichloride. So you regenerate your catalyst, and so it gets recycled over and over and over. And if you're looking at this slide and saying, man, these mechanisms are the exact same, you're right. They are the exact same. And let me prove it to you. And I can show you that in the slides here, it says that all of the electrophilic aromatic substitution, so we use EAS to represent electrophilic aromatic substitution, all of these reactions discussed in this chapter, they all follow the exact same two-step mechanism. Step 1, nucleophilic attack. You form a sigma complex, which is resonance stabilized. You go from something that is aromatic to something that is not aromatic. Then you do a proton transfer, and then you restore aromaticity, right? We call that re-aromatization. So there you go. So I highly recommend practicing this mechanism over and over. Think about it. If it's a mechanism that's really just 2 steps and it's repeated over and over and over, you can imagine that you need to know that. Okay. So there you go. There's a little bit about sigma complexes. And so far, what we have covered is chlorination and bromination of an aromatic ring. So I'm going to be, making a mistake here by rifling around on my iPad. But if we go back here, okay, so what have we covered? We've covered bromination. So for bromination, we needed bromine, okay, and we needed iron to do that, okay. And then, or you could write iron 3 bromide is fine, okay. And then here for this one, for chlorination, we needed chlorine and we needed aluminum chloride. And so now we're going to get into sulfonation to put in the sulfonic acid, and we're going to get into nitration, okay. And then after that, we'll get into these 2 reactions here in a few more slides, okay. So let's go back here. So we talked about halogenation. And so now to do a sulfonation, okay, and again, I told you this functional group here, it's got a TATC name. It's called a sulfonic acid. We haven't seen it before. It's a new functional group that you do have to be aware of. To form a sulfonic acid, what you do is you treat your aromatic ring with fuming sulfuric acid. Now, if you're saying, I know what sulfuric acid is, but what's fuming sulfuric acid? Fuming sulfuric acid is actually sulfuric acid that has sulfur trioxide gas in it. So this is SO3. This is sulfur trioxide, just a little bit of covalent compound nomenclature for you there. Now, you guys know that if you look at the SO3 molecule, right, everybody could draw a Lewis structure of it. You know that in order to make these pi bonds, there's a p orbital on the oxygen, but then there's also a p orbital on the sulfur. But they're not the same size, are they, right? Because the oxygen uses a 2p orbital, whereas sulfur is in the period below it, so it uses a 3p orbital. So what's the result? The result is that the orbital overlap between these two p orbitals is not very good. And so this bond actually has a lot of single bond character. Oxygen is more electronegative than sulfur. And so where it's orange, this is all the regions where it's delta plus, okay? And then in the middle where the sulfur is, it's very, very, very delta positive. So what does that mean? It means that sulfur trioxide is a very, very powerful electrophile, okay? So to remind you, sulfur trioxide is an electrophile, and sulfuric acid just serves as the catalyst. If you want more detail as to why sulfur trioxide is a very powerful electrophile, you can see what I was trying to explain to you on the previous slide right here, that the p orbital from sulfur is going to be a 3p orbital, whereas the p orbital from oxygen is going to be a 2p orbital. They're very different in terms of their size, so their overlap isn't that great. And therefore, the sulfur-oxygen bond has significant single bond character. Again, the consequence of this is that the sulfur trioxide is nothing more than a very, very, very powerful electrophile. So let's conclude here. So we'll put SO3. SO3 is very strong electrophile. So that means if you put it in the presence of an aromatic ring like benzene, the benzene is going to act as a nucleophile and it's going to attack it. Let's take a look. So we see the mechanism right here. This is a benzene, which is aromatic. We put it in the presence of sulfur trioxide. This is such a strong electrophile that the benzene is like, I can't help myself. I'm going to attack. Okay, so we have a nucleophilic attack. And then we form this intermediate here, which has a positive charge in the sigma-membered ring. So this is our sigma complex. Okay, and you should be able to draw all these. Remember, the sigma complex has an sp3 hybridized carbon in it. So this is non-aromatic. And then we do a proton transfer. So in the proton transfer, remember, you're in sulfuric acid, so there's going to be water in there. And so water will behave as a base. And then hydronium, which is a weaker acid than sulfuric acid, is going to be more prevalent than sulfuric acid. And so it's going to act as an acid to protonate this group here and give you, and remember, again, this is called a what? A sulfonic acid. Okay, a sulfonic acid. And of course, this is aromatic because you restore the aromatic ring. Now, again, I mentioned to you that, sulfonic acids are new to us. And if you're wondering, what the heck can I do with a sulfonic acid? What is the point? Well, we're actually not going to use the sulfonic acid to build on. Like, we're not going to add something to the sulfonic acid. What we're going to do is we're going to use the sulfonic acid to help us in our synthesis strategies. It actually helps you get to your final product in a lot of cases. Now, it turns out that the sulfonation is a reversible process. Okay, so if you use your fuming sulfuric acid that's concentrated, you throw it in there with your electrophile, with your aromatic ring. The aromatic ring will behave as a nucleophile. It attacks, you form the sulfonic acid. So again, this is the sulfonic acid. But it turns out you can remove the sulfonic acid by treating it with dilute sulfuric acid. Now, before we get into the details of this, I'm going to save that because we're going to look at that later in the chapter. We're going to talk about why you would form the sulfonic acid and then why you would want to remove it. And if you remember the idea of the protecting group that we looked at in the alcohols chapter, A sulfonic acid is not a protecting group. It's called a blocking group. Okay, so I'm getting way ahead of the game here, but it's called a blocking group. So you'll see why we use sulfonic acids in a little bit. All right, so what have we covered so far? So to review, we started out with bromination, right? We covered that. Then we did chlorination. Then we did installation of a sulfonic acid. So this one is done. And now we're going to be into installing a nitro group. So we call that nitration. Please remember that the Lewis structure of a nitro looks like this. It's actually a Zwitter ion where you have a negative charge on one of the oxygens and a positive charge on the nitrogen, right? But +1 and -1 balance out. So it gives you overall a neutral group. So nitration occurs by using nitric acid as the source of the electrophile and sulfuric acid as the acid catalyst. And it says here that it's believed that the nitronium ion, NO2+, and we could draw the Lewis structure of this guy. This is called a nitronium ion. Okay, it's believed that this is the active electrophile. Think about what I've just drawn here. This thing that's supposed to be an active electrophile. I mean, number one, you've got a positive charge on the nitrogen, so that's electrophilic enough. But then you've got a dipole going this way towards the oxygen and another dipole going this way. That means this nitrogen is super duper duper positive. So if you put that next to an aromatic ring, the aromatic ring is going to act like a nucleophile. I bet you it's going to form a sigma complex, and then we'll do a proton transfer to restore the aromatic ring. Well, before we get into that, let's talk about the nitronium ion, that ion that I drew on the last page, okay? Now, if you're wondering, where does that come from exactly? Well, when you mix nitric acid, so this is nitric acid, and you guys all recognize sulfuric acid. When you mix those two acids, it turns out that sulfuric acid, H2SO4, so H2SO4 has a pKa of around -9, whereas HNO3 has a pKa that is below it. I don't remember exactly what it is. I put here -1.4, so I just wrote that in my notes. So pKa is -1.4. And so there's a difference of 10 to the power of 7.6 in terms of acidity. So that means that nitric acid is 10 to the power of 7.6 times a stronger acid than nitric acid. So that's why sulfuric acid is strong enough to protonate nitric acid. Then you create a good leaving group, which leaves, and then you form the nitronium ion, which is a very, very powerful electrophile. This is actually a reaction we get our students to do sometimes in chemistry. I guess it's 3102. You get to try a nitration, or no, sorry, it would be 3112. Sorry, we get the students to try a nitration reaction. And so you actually have to mix sulfuric acid and nitric acid. So we tell our students, be sure to not wear your Sunday best that day because the nitric acid, and sulfuric acid can burn holes in your clothes. Anyhow, I digress. So now that we've made the nitronium ion, look at the mechanism of the benzene. Remember, this is the same old electrophilic aromatic substitution mechanism. Okay, so anywhere you see that, you're expected to know that mechanism. So we have our nitronium ion. So remember, this is called the nitronium ion, okay, which is a powerful electrophile. The aromatic ring attacks it. We form a sigma complex. So we go from the aromatic ring to the sigma complex, which is non-aromatic. Then after a proton transfer, remember the sulfuric acid and the nitric acid are in water. So water will behave as a base in that case. It's going to abstract a proton, and you do your proton transfer, and you restore the aromatic ring. So now what have we covered? We've covered bromination, chlorination, sulfonation to form a sulfonic acid, and nitration. We've covered all of these reactions. All right. So what can you do with the nitro group? I told you that the sulfonic acid, we're going to use it in a little bit as what we call a blocking group. Okay, we're going to use it to block some other groups from interfering in synthesis. But for the nitro group, right, you guys recognize this compound here. This is aniline, Okay, you had to memorize this in chapter 17. And so you can actually reduce the nitro group. Okay, keep in mind this is reduction, right? We're losing oxygen. So loss of oxygen, gain of hydrogen. So those are both definitions of reduction. So we reduce the nitro to an amine by treating it with iron or zinc metal and HCl. And then in the second step, we work it up using sodium hydroxide. Now, why would we do that? The reason why is because after the first step, keep in mind you're in a strong acid. What you're going to get after step 1 is going to be the conjugate acid of the product. So it's going to be NH3 plus. So this is called anilinium. And then after step 2, you treat it with sodium hydroxide, which is a strong base. It deprotonates and it gives you your aniline molecule. So overall, if you wanted to make aniline from benzene, you could do it in a 3-step process. You do the nitration. So remember this step here, this is nitration. Step 2 is going to be a reduction, right, from the nitro to the amine. And step 3 is just what we call a workup. Work up, which in this case is deprotonation. All right, deprotonation. So there you go. So that's the nitration reaction. So that brings us to Friedel-Crafts alkylation. So I'm going to go through a couple more reactions. I'm going to cover Friedel-Crafts alkylation with you, and there's some caveats that go with that. Okay, so I'll go over the caveats with you, and then after we finish those, we'll try this practice problem, and then we'll take a break before we get into Friedel-Crafts acylation. So we'll kind of separate the two. So far we've covered what? Let's write it down again, just to keep a tally of what we've covered. You covered chlorination, bromination, sulfonation to form a sulfonic acid, and now nitration to add a nitro group. So the next one is, you might be wondering, well, how do I form a carbon-carbon bond? Is there a way to do that? And there is. And we do alkylation by a process called Friedel-Crafts alkylation. So it's named after 2 scientists, Friedel and Crafts, and they developed this chemistry. So if you see this reaction here, you have your benzene. So benzene, you have 2-chlorobutane, and then you have aluminum chloride, which is your Lewis acid. And then you end up adding this portion, okay, onto the aromatic ring. So in this case, you're ending up with sec-butyl benzene. This is just a very specific example. But if you're wondering about that catalyst, right, your aluminum chloride, this is your Lewis acid catalyst. It works exactly the way you would think it would, right? A Lewis acid is an electron acceptor. You have 3 lone pairs on the chlorine, 1, 2, 3, 4, 5, 6, like that. So one of the lone pairs dumps into the aluminum's empty orbital. You form a negative charge on the aluminum, positive charge on this chlorine. And then you can see there's an equilibrium here between this species and this one, where you see the carbocation drawn outright. Okay, and this is going to be very relevant in a few minutes. So with that in mind, now what's going to happen is you think about that carbocation. So this is your carbocation, which is a very powerful electrophile. So now you get your nucleophilic attack. You go from your aromatic ring to forming your sigma complex, which is non-aromatic. And then after a proton transfer with the complex, with the leftover portion of the Lewis acid, I guess, you end up doing a proton transfer to re-aromatize the ring. And then, of course, you form HCl plus aluminum trichloride as well. Sorry, I'm missing an L. There you go. Plus aluminum trichloride. Now, there are some limitations to Friedel-Crafts alkylation. With everything that we've covered up till now, I never really gave you any kind of caveats or reasons why it wouldn't work or anything like that. Friedel-Crafts alkylation is a little more delicate. Let me show you why. Okay? Because you guys know all about carbocations, and you know that tertiary carbocations are more stable than secondary. Primary carbocations aren't even stable at all. And then you have methyl carbocations, which aren't stable either. So it says here, you can take a primary alkyl halide to do a Friedel-Crafts alkylation, right? This is ethyl chloride. So this is just ethyl chloride. And then in this case, we've made ethyl benzene. There's nothing wrong with this reaction at all. However, we don't draw this bond as being broken. Okay, so we don't draw this curved arrow and then just draw an ethyl carbocation the way we did over here, where we just drew the carbocation itself. Okay, we don't do that with ethyl. Why? Because you'd have a primary carbocation, which is unstable. However, this whole thing here can serve as an electrophilic reagent. And so there's nothing wrong with these reaction conditions. This works very, very well to make ethyl benzene. However, what if you had one chlorobutane, and this is your Lewis base, aluminum trichloride is your Lewis acid. What's going to happen is they're going to form a complex that's shown here, but a primary carbocation is not going to be the most stable carbocation. A secondary carbocation after a hydride shift is going to be more stable. And so what you're actually going to have is a mixture of this intermediate, which is going to react to form this compound, and then this intermediate, which is going to react to form this compound. So with alkylation, you get a product from rearrangement. So this product came from rearrangement of the carbocation, and this one came from no rearrangement. Okay, so you're always going to end up with a mixture when you start it with a primary alkyl halide. Okay, so it's not as synthetically useful as adding the ethyl group where you only get one product. There's no rearrangement that can occur. Now, there are some limitations. You know what Dirty Harry said, you got to know your limitations, okay? So the limitations to the Friedel-Crafts are this. Number one, the leaving group that the halogen is attached to, the leaving group has to be attached to an sp3 hybridized carbon. Okay, if it's on an sp2 hybridized carbon, it doesn't react. Why? Because you're not, don't draw this, okay? This is a heresy. You're never going to form a vinylic carbocation or an allylic carbocation like that, and you're never going to form an aromatic ring where you have a carbocation like this. There's no carbocations ever on an sp2 hybridized carbon, a carbon with a double bond on it. All right. The next one is polyalkylation. So once you add one alkyl groups are electron donating groups, which actually happen to activate the ring to be even more reactive. However, we'll put here in chemistry 3111, we will assume monoalkylation. Assume monoalkylation. Yes, I'm aware that dialkylation and so on and so forth can happen. But for this class, we're going to assume that we only get monoalkylation. So we would have assumed that we get this product only in chemistry 3101. Okay, so this is a rule that I guess is there for you to know, but we're not going to invoke this rule. We're just going to say all you get is the monoalkylation product, and that's it. Okay, that's how we're going to do it in our class. And then it says here, some substituted aromatic rings like nitrobenzene are just too darn deactivated to react. You know that nitro is an electron withdrawing group, and it pulls electron density away so hard from the aromatic ring, okay, that it can't act as a nucleophile. It just won't react at all. Okay? It's just, I'm not doing it. So whenever you see a nitro group on your aromatic ring, you're probably not going to do a Friedel-Crafts reaction. So that brings us to this problem here, which just says predict the expected products when benzene is treated with each of the following alkyl halides in the presence of aluminum chloride. So let's say we took benzene, okay, and we put it in the presence of chlorocyclohexane in the presence of aluminum chloride. So what's going to happen here, okay? It doesn't ask us to draw a mechanism, and I wouldn't ask you to do that. But let me just ask you guys, the carbocation that would be formed from this alkyl halide, the cyclohexyl chloride, would that undergo any kind of rearrangement? And again, I'm not trying to fool you or trick you or, aha, I got you. Is that going to undergo a rearrangement? Thanks, Rachel. You're absolutely right. Right? There's no reason for that to rearrange whatsoever. And so in this case, you're going to form one product, right? You're going to form cyclohexylbenzene. And there you go. That's it. That's all you're going to form is cyclohexylbenzene. All right. So what I'd like you to do is I'd like to take a short break, and I want you to try B and C. And then after the break, we'll come back. and we'll tackle Friedel-Crafts acylation. So once we've tried those two problems, we'll do acylation, which means we're not going to install an alkyl group, but rather an acyl group.